Hello everybody and welcome to Theorem 1.8. We are looking at page 32 in the workbook, and this theorem that we're about to look at is a really fundamental theorem about bases. Let's read it together to see what it's saying. So let V be a vector space and beta be the set of vectors u1 through un, subset of V, and the theorem says that beta is a basis for V if and only if, for each V and V, there are unique, and that word is emphasized, scalars, a1 through an, such that V is equal to a linear combination, okay, a1 u1 plus a2 u2 plus up to an un. Okay, so what this is really telling us then is that a basis for a vector space has a very special property, and that is that every vector in the vector space can be written as a linear combination of the vectors in beta in just one way, in a unique way. That's what we're trying to prove here. Now this is an if and only if theorem. We're just going to prove one direction of it, and we'll leave the other direction as an exercise. Okay, so let's see if we can prove the forward direction of this. All right, so in the forward direction, we would be assuming this, that beta is a basis for V. Okay, so we'll make that our first line. Okay, we'll go ahead and choose a vector in our vector space. Okay, now what are we trying to prove in this direction? Okay, well, we're trying to prove the part that comes after the if and only if, and that is that every vector in V can be written uniquely, and the key word again is uniquely, as a linear combination of the vectors in beta. Okay, so let's start just with the fact that since we know that beta is a basis, one property that it has to have is that it spans V. So this vector W that we chose, we know that it's possible to write it as a linear combination of the vectors in V. Okay, so let's just make that statement. Since beta spans V, the vector W can be written as a linear combination of the vectors u1 up through un. Okay. Now, how do we prove what we want to prove? Okay, well, we're trying to prove that there's only one way to write this vector W as a linear combination of u1 through un. How do we do that? How do we show that there's only one way to do that? Okay, well, there are different ways we could go about it, but one way is to suppose that we've got two different representations of W as a linear combination, and then to show that those two representations that look different must be the same. That's going to be our strategy. Okay, so here's how that might sound if we put math notation to it. Let's suppose that W has been written first as a linear combination with this form, a1 u1 through an un, and that there's also a second representation running around out there, b1 u1 up through bn un. Okay, I'm going to give this equation a name because we're going to come back to it. Okay, oh, and I should also say, just mention that the a1 through an, b1 through bn are scalars. Let's go ahead and put that here too. Okay, so for scalars, a1 through an and b1 through bn. Okay, now again, as we said just a second ago, our goal is to show that these two different looking representations are really the same. Okay, so we'd like to show that AI equals BI for all I. Okay, if we can do that, we've demonstrated that there really is only one way to write this W, okay, as a linear combination of our vectors in beta. Okay, well, let's see if we can do that. So I'm going to start by referring back to that equation star, And we'll start just with a simple observation, noting that the zero vector can be obtained by subtracting the vector w from itself. And then we're going to make use of the fact that we've got two seemingly different ways that we can write w. We've got w written one time like this. Okay, so I'm going to substitute that in for this w. A1 U1 up to ANUN. So there's my first W. But W has also been written like this, so we can substitute that second way of writing W in for the second piece. Okay, and then what we're going to do is just take the right-hand side of that equation and group things together. So notice that we've got two terms that have U1 in them, so we'll group those together and write that as A1 minus B1 times U1. And then if we went farther, we would see that we've got A2 minus B2 U2. And then we come until we get to the very last term, ANUN minus BNUN, we can group together and write as AN minus BN UN. Okay. So I have a question for you at this point. Okay, notice the equation that we have. We've got the zero vector on one side of the equation and a linear combination on the other side. Does that remind you of something that we've talked about earlier in the course? Okay, that's exactly the type of linear combination that we look at when we want to talk about linear independence. Okay, and so there's one fact that we haven't used about our set beta so far. Remember, we assumed that beta is a basis. That means that one of its properties is that it's a linearly independent set. Okay, so since beta is linearly independent, that means that this equation that we're looking at down here can only have the trivial solution. In other words, all of these coefficients, one by one, have to be zero. We can only have the trivial solution. Okay, so let's say that this way. Beta is linearly independent. So we know that each of those coefficients, ai minus bi, have to be 0 for all I. Okay, that is ai equals bi. Okay. And so, notice that that's exactly what we wanted to show. If you look back up just a little bit farther, we wanted to show that AI is equal to BI. We've demonstrated that these two seemingly different ways of writing W are actually the same, and that's our proof in the forward direction. Okay, and again, I will leave it to you to think about the reverse direction.